Hi everyone and welcome back. In this video, I will show you how to do a two-way ANOVA analysis using R. Just a reminder that the technique is called two-way ANOVA because we are studying the influence of two factors on an outcome variable. Remember that factors are categorical or qualitative variables, whereas an outcome is a quantitative or numeric variable, okay? Perfect. I wanted to mention that I already have a video about two-way ANOVA on my channel. It's titled Two-Way ANOVA Example 1. And in that video, I go into a lot of details about two-way ANOVA, like basic details of related to like what effects do we test when we do a two-way ANOVA? What hypotheses do we need to define to test those effects, right? And so definitely check out that video because I go into a lot of like basic ideas about two-way ANOVA. And I'm not gonna go into those details in this video, so I already did in that one. So definitely check that video out, okay? All right, perfect. So let's jump into art now. And first, notice that I'm using RStudio, all right? And using RStudio, I created this notebook, this .rmd file, and I did all my analysis. I included all my analysis in that notebook, okay? All right, the problem we're facing here is related to batteries. So some researchers, they wanted to study the battery lifetime, okay? So that's the outcome variable in this problem. So they wanted to know if two factors influence the battery lifetime. So they wanted to know if the material used to build the battery influence lifetime, and also whether the temperature at which the battery is used influences the lifetime. So we want to know if two factors, material and temperature, influence lifetime, which is the outcome, okay? And lifetime was measured in days. Great. So let's take a look at the data for this problem. I have the data for this problem stored in this data frame. And in that data frame, we have three columns, one for lifetime, one for material, one for temperature. Notice that material and temperature have a factor data type where lifetime is numeric, okay? And notice that we have 36 observations, so we have data for 36 batteries, okay? All right, perfect. So when we conduct an ANOVA test, we usually start by estimating, all right, estimating the average value of the outcome variable for each level of the two factors and also for the combinations of both factors, okay? And that's what I did here. I obtained the sample average battery lifetime for the three materials, okay? And I sorted the values of lifetime, all right? There you have it. So that is the sample average battery lifetime for material 1, so 83.2 days. So for material 2 is 108.3 days, and for material 3, 125.1 days, okay? So they are different, right? So the lifetime for each material is different. So the average lifetime for each material is different. But the idea is we want to know if they are statistically different, all right? So in a sample, we will always find that things are different. But are they statistically different? In other words, can we reasonably conclude that the differences that we are observing here between the materials also hold at the population level? Or in other words, can we claim that the difference that we are observing among the materials in this particular sample will replicate in other samples in the future? Or maybe no, maybe this difference will disappear. And in that case, the difference is not statistically significant, okay? So we need to find out if the difference are statistically significant, and if the difference are found to be statistically significant, then we conclude that the material influences the lifetime, right? We can get to a conclusion after we run the ANOVA analysis, which we're going to do soon, okay? All right, so now here I obtain the sample average battery lifetime for the three temperatures, okay? And again, they are different, okay? So the lifetime for each temperature is different, but are they statistically different? Well, if we conclude that they are statistically different, then we can conclude that temperature influences lifetime, okay? And to know if they are statistically different, we need to run the ANOVA analysis, okay? Which we're gonna do in a second. And finally, I always like to, and I think it's a good idea, to estimate the average value of the outcome variable for the combinations of both factors, okay? So this is the sample average battery lifetime for each combination of material and temperature. And this summary table allows us to check for possible interactions, okay? So for example, notice that for material one, so let's focus on material one for now. If we're using material one and we change from temperature 15 to 70, what happens to lifetime? We see a decrease in lifetime from 134 to 57, okay? So decrease. Now, what happens if we're using, for example, material three? If we're using material three and we change temperature from 15 to 70, lifetime barely changes at all. So it kind of stays the same. It's just a slight increase, but it actually barely changes. So what's going on here? Okay, what's going on? Does the effect of temperature on lifetime changes statistically for the different materials? Okay, so does temperature have a statistically different effect on lifetime depending on the material? Well, we conclude that yes, that the answer to that question is yes, if the interaction is statistically significant, okay? So apparently there is some difference here in how temperature influences lifetime depending on the material, but we don't know if the difference that we are seeing here is actually meaningful or statistically significant, okay? So we need to run the ANOVA analysis. All right, so let's go ahead and run the ANOVA analysis, and from the ANOVA table, we're gonna be able to conclude about the influence of each factor and the interaction. That's another table, and here we have the result for material. Here we have the result for temperature, and then the result for the interaction. So when we look at the material row, we look at the p-value, and what we do is we compare the p-value to the significance level or alpha. That's the way we know if an effect is statistically significant. We compare the p-value to alpha. Let's assume that we're using alpha 0.05, okay? So when p-value is less than alpha, we conclude that the effect is statistically significant. And in this case, that's what happens for material, okay? The p-value is 0.001, which is less than 0.05. So we conclude that material has a statistically significant effect on lifetime. And what that means is that at least two of these values, so these are the sample average battery lifetimes for the materials, at least two of those values are statistically different, okay? Well, we repeat the same thing, but for temperature. So we look at the p-value for temperature, and then we see that the p-value is 1.91 times 10 to the negative 7. That is scientific notation. 1.91 times 10 to the negative 7. That's really, really small p-value. So obviously it's less than 0.05. So we conclude that that temperature also has a statistically significant influence on lifetime. And what that means is that at least two of these values, at least two of the sample average battery lifetimes for the temperatures are statistically different, okay? And finally, for the interaction, we also see, so that's the row for the interaction, we see that the p-value is 0.0186, which is also less than alpha 0.05. So we conclude that the interaction is significant. And what that means is that the differences that we were noticing here are actually real, are statistically significant. So temperature has a statistically different effect on lifetime depending on the materials, okay? All right, guys. Now, so we run the ANOVA analysis. We know that the three effects are significant. What do we do now? Well, after we do an ANOVA analysis, remember we need to do a post-hoc test, okay? To compare the post-hoc test, allows us to compare the average value of the outcome variable for the different levels of factor 1, for the different levels of factor 2, okay? But this is the thing. You do a kind of one post-hoc test, specific post-hoc test, when the interaction is not significant, like in the problem that I did in my previous video where the interaction was not significant, and you need to do something different when the interaction is significant. In this problem, the interaction is significant, so we need to do something different. And the recommendation is that when the interaction is significant, to do the post-hoc test, you actually should do two things. First, you should do the interaction plot to visually understand how the interaction manifests, okay? And then you should do a post-hoc test where you fix the levels of one of the factors and you observe how the outcome changes for the levels of the second factor, okay? I will show you how to do that post-hoc test in a second. But first, let's do a step number one. Step number one, when there is a significant interaction, is to do the interaction plot, okay? And when we do the interaction plot, we clearly see the presence of interaction. Why? Well, in this plot, the different lines represent different materials. So the straight line is material 3, the dotted line is material 1, and the dashed line is material 2. Here we can see that when temperature, let's take a look at temperature, the x-axis. When temperature changes from 15 to 70, all right, the average lifetime decrease for materials 1 and 2, okay, materials 1 and material 2. But if material is 3, the temperature, I'm sorry, the lifetime barely changes, okay? So when temperature changes from 15 to 70, decrease in lifetime for materials 1 and 2, barely the same for material 3. So here we are observing that the effect of temperature on lifetime depends on the material. And you're going to observe the same kind of pattern if you try to see what happens when we change temperature from 70 to 125. Like one thing happens when material is 1, the dotted line, and totally different thing happens when materials is 2 and 3, all right? So that plot shows a clear presence of interaction. After that, we should go ahead and do the following. We should do a post-hoc test where we fix the levels of one factor and we observe what happens to the outcome variable when the other factor changes. So here, what I'm going to do is I'm going to do a post-hoc test where I'm going to fix material at level 1, for example, okay, material number 1. And I'm going to compare the lifetime for the different temperatures, okay? So I'm gonna see how the lifetime for temperature 15 compares to a lifetime for temperature 70, and then how lifetime for temperature 15 compares to temperature lifetime with temperature 125, okay? So I'm going to do a pairwise comparisons of the lifetimes across the different temperatures for the same material, all right? And then I'm going to repeat that for material 2 and the same thing for material 3. How do we do that in R? Well, we can use a function called EM means, okay? And to use that function, you actually need to install the package with the same name, okay? You can install the package using that function. And once you install the package, you need to load the package using the library function, okay? Let me load it. And after that, you can go ahead and apply the EM means function to get the pairs, to compare each pairs of lifetime for the different temperatures for the same material. That's what pairs means. So we're going to compare the different pairs of lifetime for the different temperatures for the same material. Let's take a look at this. There you have it. All right. So these are the results for material 1. And what do we see? Well, we see that when we compare temperature 15 versus temperature 70 with respect to lifetime, the difference between them is statistically significant, okay? Because the p-value is less than alpha. It's a really, really small p-value. When we compare temperature 15 with temperature 125 with respect to lifetime, the difference is also significant, okay? But when we compare temperature 70 with temperature 125 with respect to lifetime, the difference is not significant. And all of this is for material 1, okay? So based on what I said, we noticed that, all right, so for material 1, so this number is different than this number statistically. This number is also different than this number statistically, but these two numbers, so the average lifetime for 70 and 125 are not different, all right? So what do we conclude here? Well, assuming that we want the highest possible lifetime, so here we will conclude that the best for material 1, okay, for material 1, the best temperature is 15, okay? And I wrote that conclusion for you here. So using material 1, the recommended temperature is 15, as this combination yields the highest average lifetime. Under material 1, both temperature 70 and 125 are equally undesirable because the difference between 70 and 125 was not statistically significant, all right? And then we repeat the same analysis for each of the materials, all right? So that's the way we do a post-hoc test when the interaction is significant. Interaction plot, and then we use this, we apply EM means to do this kind of nuance analysis where we fix the levels of one factor and analyze the changes in the outcome for the other factor, right? All right, guys, that's all for this video. I hope you enjoy it. and I will see you in another video. Bye, guys.